Hello guys, so today I'm actually here with the KC from 5 coordinator. So together we want to bring to you a rundown, like a revision of thermodynamics before you take physics tomorrow. Cedric, you want to say hi to the camera?
Yeah. Hello guys, welcome to our YouTube channel, and also happy to have you guys on the channel. Enjoy the physics, thermodynamics.
Perfect. All right, so let's dive right into it. Okay, so we are going to start off our thermodynamics rundown with one of the questions I gave them in our tutorials. Well, I call that section LA's brain teasers, right? There are questions that you really need to profoundly understand the subject matter before you're able to solve them. So I'm just going to very much explain this problem while solving it simultaneously, right? Hope you follow through. Now we have at 27 degrees Celsius, 2 moles of an ideal monoatomic gas occupy a volume V. The gas expands adiabatically to a volume 2V. Calculate Roman 1, the final temperature of the gas, Roman 2, change in its internal energy, and Roman 3, the work done by the gas during this process. Okay, now this dq equals to du plus delta W. You cannot talk about thermodynamics without this equation. It's not just about school or high school, right? It's about your studies in university, your studies of thermodynamics in a university. It's about your application of your studies when, of course, perhaps you become maybe a researcher of the universe. This equation is at the beating heart of understanding the thermodynamics of the entire universe itself. All right, so we just have it down there. dq equals du plus dw. dq is actually the heat supplied to the system. du is actually the change in internal energy, and our dw is actually the amount of work that is done by the gas, because it's plus here. Now you can actually have dq equals to du minus dw if you're maybe compressing the gas now, and then you actually have to do work on the gas while you compress it, right? So this guy now becomes negative. Okay, so whenever it's positive, that's work done by the gas. Now we go on, and then we know that in an adiabatic process, our dq is actually 0, so heat supply to the system is actually 0. So we have our 0 here, but I'll just put that on the right hand side instead here. So we now have du plus dw, and our du. Now, how do you calculate the change in internal energy of any system, thermodynamic system? It's actually number of moles N times CV, which is basically the heat capacity at constant volume, times delta T, right? Change in temperature. Of course, you know that internal energy is actually a function of the temperature of that thermodynamic system, right? So yeah, we have delta T there plus P dV. So for a thermodynamic system that is isothermal, you realize that there's no change in internal energy, right? Because delta T is 0, right? Well, you'll be seeing that in a moment. Okay, so we have this expression. Now we go over to the ideal gas equation. This equation is so beautiful that any thermodynamic system you want to study usually would revolve about this ideal gas equation. Like, man, it's so cool. The applications are endless, absolutely. So we are going to come here and then just apply, differential calculus on this equation a bit. So what we're going to do is we want to differentiate this equation. So this PV is actually a product. We keep P constant, we differentiate V, we actually have P dV there. Now we keep V constant, and then we differentiate P, we actually have V dP equals to NR are all constants, right? They are not changing. And then T is actually a parameter that can change. So if we differentiate that, we actually have delta T, right? So we have equation 1 here and our equation 2 here. Now, we want to eliminate this delta T in these two equations. Look here, there's delta T, look here, there's delta T. We want to eliminate that. Now, if we want to eliminate that, we are going to come over to this equation 1 here. And then we copy NCV, right? This NCV out here, and then delta T. What is delta T from this equation 2? So delta T is simply P dV plus V dP, all that over NR, right? That's what I have here. Plus our P dV from this equation 1 equals 0. So you want to simplify that. This N goes away with this N, and then of course your CV stays there, your arrow is here. So you actually have this, and then you make, of course, LCM, you multiply all through by arrow, right? So you actually have this. Now you realize if I multiply all through by arrow here, I'm actually going to have CV, PdV, and then arrow PdV. So I can actually just take out this PdV, right? And I'll be left with arrow plus CV. I just hope you follow this small step up. Just multiply through the LCM and then simplify. You have this step plus CV VdP. So if I send in this CV, I'm actually going to have CV VdP here from this term. So equals 0. Now, of course, we know that the heat capacity at constant pressure minus the heat capacity at constant volume is actually the universal gas constant, right? So, of course, it's important for students to know why the heat capacity at constant pressure is greater than the heat capacity at constant volume. That's a passive C question. Now, the heat capacity at constant pressure is bigger than heat capacity at constant volume by a factor of R. Perhaps the difference between them is R, simply because at constant pressure, right, the gas does work against the atmosphere. So you need to supply extra amount of heat to get the same amount of, to get a unit change in temperature, right? So you need extra amount of heat. Just come to this thermodynamic equation here. I would need to supply extra amount of heat for a particular thermodynamic system that does work against the atmosphere, PdV. At constant volume, dV is 0, right? So there's no work done against the atmosphere. So all the heat you supply just simply goes to increase the internal energy of the system. And we know that heat capacity is basically what? The amount of heat required, right, to change the temperature of a substance by a unit change in temperature. So you realize that this amount of heat will be smaller if you don't have to do work against the atmosphere. That's what happens at constant volume. But at constant pressure, you are doing some amount of work against the atmosphere, so you supply more heat. That's why heat capacity at constant pressure is bigger than heat capacity at constant volume. Again, that's a passage question. All right, so we go on, and then we realize that we can come over here. Since our Cp minus Cv is R, here we actually have R plus Cv. So R plus Cv is basically Cp. So we can actually just replace that with Cp. Then we have P dV plus V Cv V dP. Now equals 0. We can divide all through by Cv PV, so that we can actually have, now if I divide all through by Cv PV, come here, divide all through by Cv PV, Cp over Cv will actually give you gamma, right? So well, gamma is just the ratio of the heat capacity at constant pressure to the heat capacity at constant volume. That's gamma here. And then P will cancel this P, and then you actually have dV over V, right? Then plus, then here your V will go away with this V, then you have dP over P, then you have Cv over Cv, which gives you 1, so you are left with dP over P equals 0. Now if we integrate both sides here, you realize that we are just going to have the integral of course your gamma here is a constant, so you have integral of dV over V, it gives you ln V, and then you integrate 1 over P with respect to P, you have ln P equals, if you integrate constant, remember that if you differentiate the constant, you have 0. If you integrate 0 now, you have a constant, right? So you have gamma ln V plus ln P equals a constant. So again, we can apply the laws of logarithms here, so that we actually have ln, okay, we can actually write this as ln V raised to the power gamma plus ln P. Now, ln A plus ln B is the same as ln AB, right? So you actually have ln PV raised to the power gamma, right? So because all of that is a constant, you realize that you actually have Vp or PV raised to the power gamma a constant. So okay, so you realize that we can actually write this as our equation 3, and this is a very defining equation for adiabatic changes. Now we can go over and use this ideal gas equation, and instead of relating pressure to volume for an adiabatic change, we can actually relate maybe temperature to volume, maybe temperature to pressure. We can relate these parameters like that. Now you realize that if PV raised to the power gamma is a constant, it means P1 V1 raised to the power gamma equals to P2 V2 raised to the power gamma, right? So again, we're going to use this PV equals to nRT, and then we realize that our P is actually nRT over V. So take this P here and substitute back in here, right? We put this P back in this expression here, this one in yellow, very important. You realize that in place of P, we're actually going to have nRT over V. So you would actually have V to the power gamma over V to the power 1, which is basically V to the power gamma minus 1. And then nR here, all of these are constant, so you have no problem with that. And then you actually have your T, so you actually have TV raised to the power gamma minus 1 to be a constant. Very important if you're relating temperature and volume for an adiabatic thermodynamic system. So again, we can also come here and make V the subject instead. So V is nRT over P. So if you put that in here again, and we simplify, you realize I would have P raised to the power 1 minus gamma times T raised to the power gamma equals a constant. So that is that for adiabatic thermodynamic systems. That's a rundown analysis there. So let's just solve this problem now. So you realize that you have a temperature, an initial temperature, you have change in volume. All right, so if we come over here, you realize that temperature is changing, volume is changing, so we're relating temperature to volume. This equation 4, that's what we're going to be using. So we actually have that here. Then of course your gamma is actually Cp over Cv. Now the gas is monoatomic, so monoatomic means that Cp is actually 5R over 2, Cv will be 3R over 2. For diatomic, your Cp will be 7R over 2, and then your CV will just be 5r/2, right? So we actually have that to be 5/3. Then you realize that our T2 will be that, if we make T2 the subject here. So we are going to have this, and then of course you simplify. Your T2 is 300 raised to the power. Okay, so we have our T2 to be 189 Kelvin. So I put this 300 because of course 27 degrees in Celsius, put it in Kelvin is 300. So the next part says change in its internal energy. To calculate change in internal energy, again is CV N CV delta T. Number of moles is 2. Your CV for a monoatomic gas is 3/2 R, universal gas constant. Change in temperature is final temperature minus initial temperature. So our change in internal energy is negative 2.8 kilojoules. Now the next part says the work done by the gas during this process. So the work done is basically for thermodynamic systems, the Q is 0. So work done is simply negative du right here. So you realize that your dW is negative du, so your dW will just be negative of this guy, which is 2.8 kilojoules. So the gas does 2.8 kilojoules of work in this particular thermodynamic adiabatic expansion. Perfect. So that's the end of this slide. Let's go on to the next part of the video. Alright, so a gas for which gamma is 4/3 is heated at constant pressure. The percentage of heat supplied used for external work is, again, we have to go back to our original definitive thermodynamic equation. So we have dQ equals du plus dW. You realize that actually this process is isobaric, right? So pressure is constant. We can actually calculate the amount of work the gas does in its expansion. So we actually have dW to be P dV. Now in this particular case, our dW is actually nR delta T. We can actually go all the way by saying that our dQ is NCP delta T, right? That's basically the amount of heat that's supplied at constant pressure. So how do you calculate the heat supply at constant pressure? N, heat capacity at constant pressure times change in temperature, right? So we can actually go on to get the ratio between the work done and the heat supplied. So you actually have nR delta T over NCP delta T. So we actually have that to be R over CP basically, right? Because you have this N goes away, this delta T goes away. R is basically CP minus CV on CP. So we actually have that to be, so if we distribute this, we actually have 1 minus CV on CP, and V on CP is actually the reciprocal of course the CP on CV, because this gamma here is actually the ratio between the heat capacity at constant pressure to the heat capacity at constant volume. So we have the reciprocal of that gives you the CV over CP, so you have 3/4 instead. So you have that, and then you have 1/4. So again, the percentage of heat supply used for external work, right, is basically, multiply this by 100%, you actually have 25%. So our answer is A here. Okay, so GCE 2020 is our next example. So you have 2 kilograms of water has a volume of that when in liquid state at 100 degrees Celsius. When water is completely changed from liquid to vapor at 100 degrees Celsius under a constant atmospheric pressure of 1 atmosphere, the volume increases to 3.38 meter cube. How much work is done against the atmosphere as the water changes into vapor? What is the change in the internal energy of the water during vaporization? Okay, so again, we want to look at the work done, right, in this particular thermodynamic process. So to get work done, of course, speed dV. So work done there, the constant pressure is 1 atmosphere, which is basically 1.01 times 10 to the power of 5, and our change in volume is final volume, which is 3.38 minus initial volume. Perfect. So we actually have our work done there to be 3.4 times 10 to the power of 5 joules. Now the one also says, what is the change in internal energy of the water during vaporization? Let's use our famous thermodynamic equation, dQ equals du plus dW, right? So we actually come over and then we say, now mind you that if in the exam they wrote du equals to dQ plus dW, you realize that if you want to put it back in its original state of dQ equals du plus dW, dW would rather be negative there. Actually, that's 2019. So if you have du equals to dQ plus dW, then that's not work done by the gas, that's work done on the gas. Okay, so the statement that dW will be the work done by the gas will be wrong. So whenever I have dQ equals to du minus dW, again minus because it is work done on the gas, or du equals to dQ plus dW instead, then you realize that you put it in this form, dW will be negative. Again, it is work done on the gas, not by the gas. All right, so dq equals to mLV, right? That's a heat supplied at this change of state, right? Mass of water times specific Latin heat of vaporization. So our dq mass of water, of course, is 2 kilograms here, and then we plug that in. Our specific Latin heat of vaporization is, of course, 2.26 times 10 to the power 6 joule per kilogram. So we actually have our dq to be 4.52 times 10 to the power 6 joules. Now with dq, we actually know that our du will be dq minus dw, right here. So we actually know that du would be our dq. This is our dq here, 4.52 times 10 to the power 6, and then our dw is actually this. We plug those in, and then our du is 4.2 times 10 to the power 6 joules. So that is the solution to GCE 2020 thermodynamics. I hope you enjoyed the video, guys. Subscribe, like, and I wish you all the best in your exams tomorrow. I think you're good enough to ace physics, right? Just get your confidence up, walk into that hall, and absolutely rock it, right? Own the hall, guys. All right, all the best. During an isothermal change, okay, so dq is du plus dw, our famous thermodynamic equation. dw is basically work done by the gas. Now dq is actually du minus dw because work done on the gas, right? So work done on the gas is actually negative. So for an isothermal process, of course, you realize that our dq is actually nc sub v delta t plus p dv, right? Because delta t is actually 0, right? Again, that's why isothermal process is temperature does not change. Iso means constant, thermal means, of course, temperature. So isothermal means constant temperature. So our dq heat supply. Now you can actually calculate how much change the internal energy system does by simply getting the number of moles of that particular gaseous system multiplied by the heat capacity at constant volume, right? Multiplied by the change in temperature. That gives you the amount of internal energy changed over the particular thermodynamic system between those temperatures T1 and T2. So plus PdV, of course, that's work done by the gas. So you realize our dq is actually just PdV because it's delta T is 0, right? So here changing internal energy is basically just 0 because temperature is not changing. So again, we want to integrate, right? We just want to integrate PdV, right? Because if work done is actually PdV, slight change in work will simply be P times slight change in volume, right? So we integrate both sides. We're going to have integral of slight change in work equals integral of PdV. Now again, what is P? P is ideal gas equation PV equals NRC. Again, if there's any teacher who teaches you and does not bring out the beauty of this particular equation, it's almost criminal in nature, guys. It's really almost just, he's just stealing a living basically. So again, P here, we can actually have P to be nRT over V so that we can integrate that. So we have nRT over V, integral of that from V1 to V2. So our work done is actually nRT ln V, right? So you put in these limits V2 minus V1, you have that, and then you have work done to be nRT ln V2 and V1. Okay. Now, because for an isothermal process, PV is actually a constant. Come here. You realize that N is a constant, R is a constant, T is a constant because isothermal means temperature is not changing. So all of these guys are constant. So you realize that your PV will be a constant. So P1 V1 is equal to P2 V2. So if I actually have V2 over V1 here, that's identical to P1 over P2. So whenever you are given an isothermal process like that, you need the work done nRT ln V2 over V1 or nRT ln initial pressure over final pressure, right? Or final volume over initial volume. So that's work done there. Now let's go over to an isovolumetric process. So we actually have dV to be 0. Isovolumetric means constant volume, right? So again, if you don't want to call it isovolumetric, you call it ISOCHORIC thermodynamic process, right? So again, if our dV is 0, you realize our work done is basically 0. Like here, work done is 0 joules. dq is basically nc sub v delta t, right? So we come over here, and for adiabatic processes, our dq is 0, right? Because the total heat you supply to that thermodynamic system is basically 0. Heat supplied or leaving the system is 0. Now, for if adiabatic processes, are such that no heat enters or leaves the system, there should be conditions for that particular process to occur in physics. And what are those conditions? There are two major conditions you'll be tested on. Number one is you really want that thermodynamic system to be highly lagged, right? It should be made up of insulating walls such that no heat leaves or easily enters the system. Number two condition is that the adiabatic change should be very rapid. So you want that system to occur, or that particular thermodynamic process to go as fast as possible. Now, why is as fast as possible? Because you don't want any heat to be lost to the environment. So you want to make sure that it occurs as fast as you possibly can, right? So those are the two conditions. Now for isothermal, just to show you conditions that are required for isothermal processes. Isothermal, you rather need a highly conducting material, all right? Good. Because now for isothermal, you want to keep the temperature constant, the gas is permitted to do work, and then the system is actually permitted to lose energy to the environment or to gain energy from the environment. So you want to keep temperature constant, so you actually want to keep this term 0, right? Because du is actually a function of the change in temperature, and then you're supplying heat and then you're doing work. So you want to make sure that all the heat you supplied has all the time for the gas to absorb and then do work, so that none of it goes to increase the temperature of the gas. If you just supply heat as quickly as possible, then you realize the temperature of the gas will easily increase. So now for isothermal processes, they will have to occur very slowly, so that you slowly add heat into the system, and then the gas slowly uses up that heat to simply do work and expanding without increasing its temperature, right? Because then you'll be changing the internal energy. So that's isothermal processes. Two conditions. Again, highly conducting, so that you can easily add this heat into the system. Number two is that it should be very slow, so that all the heat you add into the system should simply be used to do work without increasing the internal energy of the gas, right? So we come over here. Since our dq is 0, you realize that our dw will be negative du, and then our dw is actually, because du is actually mc of v delta t, right? That's changing internal energy of the gas. So again, that's just it. And then I come over here, I just indicate the graphs. Now this isothermal, this adiabatic, you realize that the PV graph for adiabatic processes is steeper. You see that? Like it's a lot steeper. Yeah, you want it to occur as fast as possible, right? Good. So isothermal processes, I mean, they take a lot more time to occur. The isobaric, I mean constant pressure, that's why you have a constant line from a particular pressure here all along. Isochoric, constant volume, that's why it goes up. Now if you look at this isothermal process, now this is GCE 2020, right? Question 11, you actually had a set of isothermals like that, and they ask you what is the relationship between their temperatures. Now remember that PV is a constant. Come over here. PV is a constant for isothermal processes. So if I draw a constant pressure line all along to these guys, right, you realize that constant pressure would yield different volumes. So for this guy like that, the volume will be here. For this guy, the volume will be a lot higher. For this guy, the volume will be highest. So the product of PV for this isothermal is actually highest, right, for a particular given pressure you choose. So it's actually highest because its own temperature is highest. Remember that PV is nRT, nR are constants, and then T is also a constant. But then T3 is just highest. So the product of P and V would be highest for this T3 here. So this isothermal is at the highest temperature, this T2 is at the next highest, and then this T1 is at the least temperature, right? So T3 is greater than T2 is greater than T1 here. Perfect. So those are analysis. I hope you enjoyed it, and I wish you all the best in your exams tomorrow. Honestly guys, working there and rock physics, and come over for concours classes. We'll be meeting you guys soon and preparing you for your tertiary education and your futures. But hey, again, you have the A level to beat. All the best. You have my luck. Thank you for watching. You can share it to your friends, and yeah, thank you. Stay curious.